Hi there, welcome back. Previous video we just sort of introduced that framework between position, velocity, and acceleration, which you were probably somewhat familiar with, and probably wasn't too hard just to extend that concept from 2D. So now, having established that, let's go ahead and apply it. So I'm going to go ahead and bring back that graph that we made just to show us kind of how all those functions connect. And what we're going to do is kind of go through a problem algebraically, and we're going to use some MATLAB on the side, so whichever one of those you want to follow, and at the end we'll look at it graphically really quick as well, just to make sure we're on the right track. Alright, so here's the problem. A mathematical bug is flying through 3 space. We only have a few pieces of information about the bug's motion. We know that at all points in time the bug's acceleration vector is a of t equals bracket 6t to 12t, and we know that the velocity at time t equals 1 is equal to the vector 4 to 11, and we know that at time t equals -1 the bug is located at the point -3, 4, -7. What we want to do is find the bug's location at time t equals 3. So we know from our graph here we've got 3 relevant and related functions, namely position, velocity, and acceleration, and we know that they're related by these derivative and integral relations in the chart. But as you may recall from similar problems in 2-space and integral calculus, knowing one of these functions doesn't necessarily specify all of them. Let's say if we knew the position function, yes, we could find the exact acceleration function just by taking its derivative twice. However, if you go the other way, if you start with acceleration and you want to find the position function, you can do that, but you need a little bit more information because, as you recall, there are an infinite number of valid solutions when you integrate, and we're going to integrate twice. So we're going to have to narrow that family of solutions down twice, and that's where these conditions come in. We're given 2 conditions for the velocity and for the position, and that's going to help us narrow down from that family of solutions to those specific solutions by solving for constants. So we are given one function, a of t, and 2 conditions which will allow us to find our position function r of t. So first we can integrate our acceleration function, and of course this is going to give us a family of velocity function solutions, and we're going to have to solve for that constant c. But notice now that constant c, we're in 3 space, and that constant c is actually going to be a vector because it's got x, y, and z components. Alright, so we integrate our acceleration function and we end up with the velocity vector function of 3t squared, 2t, and 6t squared. And to solve for that c component that we got to add on to it, we're going to set our velocity at t equals 1 equal to 4 to 11 according to that condition we're given. So all we got to do to solve for that c is we just plug in 1 for time, and this yields the equation, our vector 3, 2, 6 plus our constant vector c is equal to 4 to 11. So we can just see that what each of those c components has to be to make this equation correct. So that x component of c has to be 1, that y component of c has to be 0, and that z component of c is 5. And if we define c as the vector 1, 0, 5, that equation works. So now we know what our c is, and we can plug that back into our vector function, and now we've got it. Alright, so we can then go through a very similar process by integrating the velocity function we just found to solve for our position function. And of course, again, this gives us a family of position functions, and we have to solve for that constant. We'll just call that d this time. So to solve for d, we do this similar process. We set r of -1 equal to the vector -3, 4, -7 according to the condition we were given. And plugging in -1 for t, we get this equation where the vector of -2, 1, -7 plus our constant vector d is equal to 3, 4, -7. And doing the same process, we know that the x component of our d vector has to be -1. The y component of our d vector has to be 3, because of course 1 plus 3 is going to give us that 4. And we know that our z component of d is 0 because that -7 just stays the same. So now that we've got our d, we can go ahead and add that on to the position function that we solved for. So we end up with this final equation for our position function, where the x component is t cubed plus t minus 1, the y component is t squared plus 3, and the z component is 2t cubed plus 5t. So we're getting really close now. We finally solved for our specific position function. All we need to do now is plug in 3 for that function and see what we get. So plugging in 3, we just crank through some numbers here, and we end up with the vector 29, 12, 69. So it's hard to know just from this if that makes sense. Algebraically, there doesn't seem anything wrong with it, but let's go ahead and check that out graphically just to see if we're on the right track. All right, so if we go into Calcplot 3D, we can plug in the space curve, which we see here, and what we want to test is the points we were given. So we were given the position at t equals -1 initially, and we were given that that's equal to -3, 4, -7. So if we change our time here to -1, we see that our trace should overlap that position of -3, 4, -7 in blue. And it does, so that checks out. We're good there. Now let's check that final answer we got. So if we go ahead and ratchet our t up to 3, we should see that when t equals 3, it traces over that point 29, 12, 69. That was our final solution, which is shown by that magenta dot. And we see that it does trace over it, so it looks like this checks out. So graphically, we just kind of confirmed that this makes sense. And that is how we can use some calculus and algebra to solve a 3-space problem involving position, velocity, and acceleration. So I hope that makes sense. I hope you're still having a great day. And we'll go a bit further with this next video as we explore the TNB framework. So stay tuned for that.